Okay, so we were at this step. Okay, now you may want now to see, okay, what is the geometrical point of view, okay, which is the sense of changing this power meter, okay, and why we have to minimize this stuff, this term, okay. Again, this is the optimization function. We have to find this coefficient that minimizes this function. This is the part related to the cost, okay? So how much samples are far from the boundary of the classes, okay? And this is a regularization term, okay? Which is just the sum of the squares of the coefficients. Okay, now, so the meaning here is the lower the coefficients, the better, right? Why? So, to understand this, we can simplify a bit things and have a look to this situation, okay, in a b-dimensional space, so we can visualize stuff. And you have to remember what does it mean making a product vector in a product, okay? So, in a general term, if you have two vectors, A and B, okay, in a b-dimensional space, okay, so these are b-dimensional vectors. A1, A2 define coordinates for vector A, B1, B2 the coordinates of vector B, okay? Then if you want to calculate the length of a vector, okay, the norm, okay, this is the way. Okay? When you do a product, the inner product of these two vectors, so you multiply A times B transposed, okay? This is what you do, okay? So this is the inner product of the two vectors, okay? And this is equal to, in a geometrical point of view, okay, to the length of vector B times the length of vector A times the cosine of the angle between the two vectors, okay? If the two vectors are orthogonal, this is equal to 0, okay? If, okay, you can also define things in this way, okay? This is the inner product between the two vectors, okay? P here indicates the projection of vector A on vector B, okay? So if we define P as the length of vector A times the cosine of alpha, okay, then the inner product is equal to P times the length of vector B, okay? And in a geometrical point of view, P is this stuff. It's the projection of this vector on B, okay? Okay. If we have this situation, okay, so alpha is higher than 90 degrees, okay, then P is negative, okay, but then we have the same situation, okay, so P is the assigned length of the projection of vector A on vector B, okay. This is needed because then we can play a bit with the super vector machine equations, okay? So, if you remember, we said, okay, if we put a very, very high cost value, okay, then we can assume that the first term in the optimization function is equal to 0, okay? Which means, if you remember, all samples of red class 1 have a linear combination higher than 1, and the samples of the other class a linear combination lower than -1. Okay, this was from the beginning. In this case, okay, we reduce the optimization function to this, to the minimization of this stuff. Okay, now let's play a bit and simplify stuff. So imagine we just have two variables. Okay, so we are in a two-dimensional space, and let's say that we impose that B0, the intercept, is equal to 0. Okay, so this is this stuff. Okay, we have to minimize the sum of the coefficients for the first variable, the sum of the squares of the coefficients for the first variable and the second variable. Okay? And this stuff, okay, is exactly this stuff, and so we can write this as this stuff here. Okay? And this is the squared length of the vector B, the vector of your coefficients. Okay? So we have to minimize the length of this vector. Okay? This is what super vector machine tries to do. Okay? Minimize the squared norm length of the coefficient vector. Okay? What does it mean in a geographical point of view? Okay, now let's go back to the inner product we have seen before. Okay, and the projections. Okay, because it depends on that. Let's do it slowly. Okay, so here you have, okay, a graphical example. So let's say we have one sample. Okay, we have two variables. Okay, we are simplifying just to see this stuff in a graphical way. We have two variables. We have one sample. This is the value of variable number 1, the value of variable number 2. Let's say this is the vector of the coefficients. Okay, these are the two coefficients, B1 and B2, found by super vector machines. Okay, these are the two vectors. Okay, and then we do a linear combination between sample and the coefficients. We get a linear combination and we classify, okay, if the linear combination is higher than 1, we classify the sample in class 1, otherwise in class 0. Okay? Okay, so here we want to minimize, okay, the length, the squared length of this vector. Okay, this is the linear combination. Okay, this is the graphical situation, okay, of a generic sample. Okay, now if you remember the properties of the inner product, okay, we can apply the same here. So this is the linear combination, okay, as we have seen from the beginning. This is the linear combination between the coefficients and our sample, a generic sample, okay? And this is what we use to classify and to calculate the cost. Now, we can write this, okay? This is the B vector times the transposed vector of the sample, but this is equal to this stuff. The vector of the samples times the transposed vector of the coefficients is exactly the same, okay? But this is, okay, if you look at this, okay, we can write this as this stuff, okay? Can you see the analogy? Where this is the projection of my sample on the vector, on the vector of the on the coefficient vector. Okay. This is x times the cosine of this angle. Okay. And this is exactly, this is the linear combination. Okay, we can write this stuff as this one. Okay? Of course, this is true for any given sample. Okay, so now I'm showing you this sample, but of course then we have different samples in this space. Now, is it this stuff clear? Reaction? Okay. Now let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9 samples. 4 red samples, 5 blue samples. We want to do a classification model, okay? And we want to do it with super vector machines, okay? So, super vector machines tries to define a boundary with a large margin between the two classes. Okay? We put a very high cost value. So, we want this to be true. Okay? And so, which is the decision boundary found by a super vector machine? Let's say that we want to evaluate this threshold. This is not a threshold, this is a boundary. Okay, this class boundary. I mean, you can see this is not a good solution. Okay, because here you have a very small margin, right? Okay. In fact, this will not be the solution found by super vector machine. Why? Because first, okay, here we have just 2 variables, okay? Do you remember we imposed that we have no intercept? This means in the super vector approach that the classification boundary crosses the origin of your space. Okay? Now, in this case, if this is the decision boundary, okay, then the coefficient vector is orthogonal to this boundary. Okay? So, let's say you have these 2 classes, okay? You want to use super vector machine, okay? Where do you think super vector machine will choose a nice boundary which maximizes the margin? I think, let's use another color. I think you will
Davide,
yeah.
can you move a little bit the...
Yeah.
Yeah, perfect. Oh, beautiful.
I think it will choose something like this. Okay, to maximize this margin. Okay, if this is the boundary between the classes, then the coefficient vector will be orthogonal. Okay, this one. Okay, this is the same situation, but with a really bad boundary, okay, between the classes, because there the margin is not so large. Okay? Okay. So why super vector machine would not choose this stuff? Because let's take one sample at a time. Okay? Let's start with this sample. Okay? Now, this is the coefficient vector. This is the sample vector. This is the projection, okay, of this sample on the coefficient vector P. Okay? You remember? Okay? We want this, okay, to be, we want this to be high, this linear combination to be higher than 1 for the red samples, right? But we can write this exactly like this, okay? The projection of the sample on the coefficient vector times the length of the coefficient vector, okay? So, intuitively, this quantity for the red class must be higher than 1, okay? If this is small, because we want to minimize it, this must be high, right? We want this to be higher than 1, at least, okay? This must be small. That means that this projection must be high, which in a geometrical point of view, okay, is the opposite of this situation, okay? Here, for this sample, the projection is very small, okay? So, in order to have this higher than 1, this should be very, very high. But we want the opposite, okay? And we want the opposite to force these projections to be high, which means having a better margin, okay? Have a look to, let's take this sample now, okay? We calculate this for every sample, okay? Let's take this one, okay? This is a blue sample, so the linear combination, okay, which is equal to this stuff, must be lower than -1, okay? Now, this is the sample. This is the projection of this sample on the coefficient vector. And again, this is very, very small, okay, and negative. So, here, we are in the same situation as before, okay? If we want to minimize this, this must be higher, okay? So this is not a good solution. This is not a solution that super vector machine will find, okay? If you look at this data, and you want to separate them with a boundary which crosses the origin, probably this is the best one, right? Something like this. Okay, wait. Can you see the difference now? This is another decision boundary, okay? Blue, red. But here I have a large margin, okay? Now the same samples as before. This is the projection of this red sample on the coefficient vector, which is much higher than before, okay? So that means that this is going to be higher than 1. Here, this is the projection of this sample on the vector of the coefficients. Again, this projection is higher than before, okay? And negative. So, I'm in this situation, okay? So this is the consequence of doing this, using this regularization term, okay? You minimizing the squared norm of the coefficient vector, you get a good margin. So a good separation distance between samples and the boundary between the classes. Okay? Here, the magnitude of the margin okay, for separation is proportional to the projections of the samples on the vector of the coefficients. Okay? And so this situation is much better than the one before. And this will be probably the decision boundary that a super vector machine would find for this data set. I mean, of course, this data set is very stupid, okay, very few samples, but this is the principle used by super vector machines to define the boundary. Okay? Here, these projections are higher than before. Okay? That means that this can be lower. Okay? To respect these constraints. And having small coefficients is what we want. Okay? You can also look in the opposite way. We put very low coefficients so that this projection must be very high. Okay? And so you have this separation, and you associate this margin to the separation. Okay? I don't care about this, it's always the same thing. Now, I hope this geometry, maybe, the first time it's not so straightforward, but if you look at it tomorrow or the day after tomorrow, I think it can help, okay, to understand what's going on. So, to repeat, just to do an abstract, short description. Okay, this is the optimization function which helps super vector machine to define the decision boundary with some margin. Okay, so some distance between samples and the class boundary. Okay, we want to minimize this stuff. Okay, these are the cost functions. Okay. And these are the linear combination of the set of coefficients found by super vector machines. Okay? Now, we have said that if we use a very high C value, okay, then we can think this must go to 0, okay? And so the optimization function is reduced to the minimization of these coefficients, okay? This is true, okay, when you have very nice separations, like in this case, okay? Here we are in a very good separation, where it is clear that there is a distinction between the red and the blue class, okay? And if you look here, okay, this is the decision boundary. These are our samples. And can you see all these samples will have a cost equal to 0. All the blue samples, okay, are, how can I say, behind the margin, which means that the linear combination will be always lower than -1, which means that all their costs will be equal to 0. All the red samples are behind the margin, okay, which means that all the cost values for the red samples will be equal to 0, and this sum will be 0. Okay? This is the best case, but it's not the usual one. Here, can you see? Okay? In this case, this is the classification treatment, okay? And this is the margin, okay? And this margin is equal to 2 times P, okay? Which means that this margin is equal to 2 divided by the length of the coefficient vector, okay? So, the lower this is, the higher the margin. Okay, it makes sense. we want in the optimization function, we want to reduce this. Okay, look at this term. We want to reduce this because then we have a larger margin. It's the same thing we have seen before with the geometrical approach, but it's exactly the same thing. Now, when you don't have, this is the real case, when you don't have perfectly separable classes, so you have an overlap, okay? Of course you can use super vector machine, okay? Of course, I mean, this term will not be equal to 0, okay? So, in the optimization function, you will have to minimize the coefficients, but also to minimize this part, okay? And this is, for example, a real case, okay? Here you have a case where you have red and blue samples, okay? Imagine always to have two variables, okay? So we are looking at a two-dimensional space. Can you see there is an overlap, right? It's not possible to perfectly discriminate the two classes, unless you do a lot of overfitting, but we will see it later, okay? So you can do whatever classification here, you will have some errors as usual, okay? But still, okay, super vector machines try to find coefficients that minimize this stuff, okay? It may, so they may find this class boundary, okay, with this margin, okay, which means that the coefficient vector will be orthogonal to this stuff, okay? And this is the best margin they can find, okay? The best way to have the samples as far as possible from the decision boundary, okay? If the decision boundary is here, everything on this side will be classified as, if I have a point here, will be classified as blue. And everything on this side as red, okay? So, this is one error. This is one error. This is one error, okay? Now, let's check if you understood, okay? This is the decision boundary, okay? Which is this point, okay? The 0 point. We said the decision boundary is 0, okay, and then we do the linear combination. If the linear combination is higher than 0, then we classify it as red, otherwise as blue, okay? This is the margin, okay? So, let's take, this is the red class space. Let's take this sample, okay? This sample will have cost value equal to
1.
no,
0.
0, okay? Because we are behind the margin, okay? This value will have a cost value equal to 0 because it's on the margin. This sample is okay because it's in the red space, but it will have a cost value higher than 0, okay? We are around here. This one, okay, this is dramatic because this is in the blue space. It will have a cost higher than 0, yes, and it will be very high, okay? So, imagine SVM to find a boundary to reduce all these costs, okay? The same for the blue class. This blue sample will have a cost? No, because it's behind the margin. This sample, the same. This sample is okay, but it will have a cost because it's very close to the boundary. And it's, how do you say, in front of the margin, okay? This sample, it will have an higher cost, okay, because it's in the red space. And this, even higher, okay? So you can look at the cost as the length of these errors, okay? and we try to minimize it. That's all. Okay? Yeah.
I might have missed one. How do you define the cost function? Like here they seem
You decide it.
linear.
You decide it.
So because if you choose something which is more steeper, let's say, you impose an additional constraint on the minimization. I assume that the minimization goes faster, let's say, or no?
Let's say that, okay, this is a term you have to decide, okay? So again, the best thing is try and error. But we will see it later,
Sometimes
But-
this is
but we can see it even now, okay? So if you use a very high values,
I was referring to the cost.
this one.
This one, yeah.
Okay, what do you say? How do you,
How do you define that function?
it's,
It's
defined in this way.
it's linear.
Yeah.
Because
I mean, maybe then, I've seen it linear. Maybe then people for sure try to change it in other ways. Yeah? But then linear means you don't have to choose anything. Not linear means that you have to decide how not linear is, and then I don't know. Okay, but let's say this is the classical way. Okay, but of course people probably propose new things. Okay. I was also referring to this term. Okay. If this is very, very high, okay, then this must be, you say, low, okay? That means that if you want to reduce this stuff, this margin must be smaller. Because in this, because if you reduce this margin, the cost will decrease. I put 10,000 here, okay? So I need this sum to be low, okay? How can I reduce for example, the cost of this sample and this sample? I put a smaller margin here, and the cost will be lower, and this will be decreased, okay? If C is low, you have the opposite, okay? You can have a larger margin. Okay, we will see it later, but having a very, very high C can bring you to overfitting. Okay, especially because now we are looking at linear supervector machine, which is okay. When you use it in a non-linear way, then things get a little. You can have a lot of advantages in terms of separability, but you have to pay attention what you do when you optimize this stuff. Is this enough clear? Yes. But another thing, why it is called supervector? Okay, because it's the same situation as before. Okay, but I have highlighted only samples which have a cost higher than 0. Okay, all these samples are called supervectors. Okay? So all the samples which have a cost higher than 0. That means that those are the samples which lie on the boundary, okay, or behind the boundary. Okay? So these are supervectors, this is a supervector, and all these are supervectors. Okay, for the red and the blue class. Okay? And only these samples are used then to estimate the model. Okay? Is enough here, at least the idea of supervector machines, okay, to have a large margin, okay, between the two classes. this is the idea. Okay? Now, SVM are applied a lot because, as I said you in the beginning, they can be adapted. As you see now, I mean, the decision boundary is linear, okay? But when classes have not a linear separation, okay, this stuff, super vector machine, can be adapted to work as non-linear classifiers, okay? So, if you have if you have an example like the one I was showing you, okay, linear classification is enough. So linear super vector machine or discriminant analysis is super, or PLSDA is okay. Okay, there is no reason to apply fancy neural networks or whatever. But if you are in a situation like, I don't know, like this one, okay, then, with a linear separation, you will have errors, okay? Probably the most natural way here to separate is with a non-linear boundary, okay? But when you apply these methods, you really have to take care, because the reality, this is not a real case study, okay? Usually, you always have some overlaps, right? And this stuff is very powerful, so if you do not pay attention, okay, when you fit non-linear super vector machine or whatever non-linear method, then you may find a separation like this one.